So here is the actual lab report. It is our second lab, and it's looking again at the respiratory exchange ratio. Some conversions, some you already know, but some conversions you'll need to work on some of the data. And I went and looked in our exercise physiology lab and looked at our computer system from that metabolic cart. And that data is downloaded in Excel, and it's a big spreadsheet of data and a lot of data to work with. So the data that I'm sharing with you in this lab report, I've averaged different times periods in this big Excel spreadsheet. So the respiratory exchange ratio, it's abbreviated RER, and even more commonly, it's abbreviated simply as R. So the R value is this respiratory exchange ratio and can give an indication of fuel utilization. It is also known as the RQ, which is the respiratory quotient. It's a slightly different measurement, and we'll explain that later. But so all these three, the respiratory exchange ratio, or RQ, RER, or R, they all mean the same thing. And the calculation that you will do in this lab, it's simply a ratio. It's the ratio of the volume of CO2 produced. So as someone is exercising, how much CO2 is coming out divided by how much oxygen is coming in. So it's a ratio of VCO2 produced divided by VO2 consumed. And the units cancel each other out. So this respiratory exchange ratio does not have units. It's just a ratio of CO2 produced over O2 consumed. So let's look at two examples. And remember, this RER gives an indication of fuel utilization. Let's look at two examples. One example is burning or using a fatty acid called palmitate, and using that fatty acid, send it into the mitochondria where it's completely oxidized. It's completely burned up. And so the equation to burn up this fatty acid called palmitate, which is a big long chain fatty acid, has 16 carbons on it. It would take 23 oxygens to burn that up, and it would produce 16 CO2s. So remember, the formula for respiratory exchange ratio is CO2 produced over O2 consumed. So it is 16 divided by 23, 16 carbon dioxides divided by 23 oxygens, and that value is 0.7. So if the RER value is near 0.7, then one is burning predominantly fats as a fuel. Great. Let's take another example. And you know this chemical formula, which is a formula for simple glucose. Glucose is C6H12O6, and it takes 6 oxygens to completely burn or oxidize that glucose, and it produces 6 CO2s. So the ratio again is CO2 divided by O2. 6 divided by 6 is obviously 1. So if the RER value is close to 1, then you're burning predominantly carbohydrate as a fuel. Great. So, and I explained that in the second page of this lab. So I'm going to ask you to look at some data in this spreadsheet that, or averages of data from a spreadsheet, and I copied it into the lab. And then determine the R value, and then determine the percent fuel utilization. And we use what's called a ParvoMedix open circuit metabolic cart. And again, it's worth it to look at those videos from students where they explain this metabolic cart. And basically a mouthpiece or a mask is placed around the volunteer, and we can collect a sample of air, and we measure that sample of air for the percent of oxygen expired, the percent of CO2 expired, and then the total volume of air that is leaving this volunteer. And with those three variables, the metabolic cart can calculate out VO2 produced, or VCO2 produced, and VO2 consumed. So here's the spreadsheet of data. So here's the patient information. You may need to know his body weight to do some of the calculations. So he was 79.5 kilograms. And here are the conditions over on the left-hand side of this spreadsheet. We had a resting condition, light, moderate, and hard exercise. So really 1, 2, 3 different exercise intensities. And we had 3-minute stages. So he rested for 3, and this was on a bike. So he biked easy for 3, moderate, and then hard exercise for 3 minutes. These are the calculations for the workload, and the units are a little bit funny. They're called kilogram meters per minute. It's actually a work rate. And I'm going to ask you to calculate out the workload in watts, and that's a little bit more typical measurement of work, or actually a measurement of power. And the conversion is at the front of this lab, where 1 watt is equal to 6.12 kilogram meters per minute. So by using that conversion, you can complete this part of the data table, convert these workloads into watts. I also entered in the absolute oxygen consumption. So this is the person's total oxygen consumption in liters of O2 per minute. That is this column. And then if we skip over a couple columns, here is the VCO2 produced. So how much oxygen this person was consuming in those same units of liters of O2 per minute. So remember that the respiratory exchange ratio, it is a ratio of VCO2 produced divided by VO2 consumed. So you're simply going to take this number and divide it by this number, and that will be your R value. And remember, R values, this respiratory exchange ratio, the range of these values should be around 0.7 to around 1. So if you got a respiratory exchange ratio of 10, for example, look at your math or look at the numbers, because that's not possible. So the values should be around 0.7 to about 1. Okay, fine. So you'll calculate respiratory exchange ratio. You'll also convert. So you need to convert these liters of O2 per minute into milliliters of oxygen per kilogram body weight per minute. So in lab 1, you successfully did the conversion the opposite way of mils per kg per minute to liters per minute. Now I'm asking you to go from liters into mils per kg per minute. So you know that 1 liter is equal to 1,000 milliliters, and then you'll need to divide out by this person's body weight. And we estimated VO2 maxes, so you correctly said that a typical average VO2 max for college-age individuals, around 35, 40. So if this person is working pretty hard, this value should be, we're not exactly sure, but maybe 30, 40 milliliters of oxygen per kilogram body weight per minute. And this value should be about 3.5. So a resting VO2 in relative terms, in mils per kg per minute, this value should be about 3.5. And 3.5 is equal to 1 MET. So MET stands for metabolic equivalent. So it's how many multiples of a person's resting metabolic rate. And I haven't done the math. I don't know what this person's resting VO2 is, but it should be about 3.5 mils per kg per minute, and that is equal to 1 MET. So you also need to complete this column in terms of how many METs this person was exercising. Great. So there's the data table. So complete this data table. And then there's one graph I would like you to make. And I would like you to make a line graph or maybe a scatter plot of the respiratory exchange ratio, the R value, on the y-axis, so the vertical line. And then you can decide, you can do it by time or you can do it by power in watts on the x-axis. And you'll just draw one line in there. And then that line would represent the R value at rest and at those 3 different exercise intensities. And we predict it's going to start off low, like around 0.7 or 0.75. And we predict this line is going to go up to, approaching 1.0. Great. If you want to make an extra credit graph, I would love to see the graph of the crossover graph of fuel utilization using the data from this lab. So that will be using the percent energy from fat and the percent energy from carbohydrate. And you will find those data from this data table at the bottom of our graph. So here's an R value. And so remember, at an R value of close to 0.7, a person is burning 100% fat as a fuel. Oh, there, 100% fat as a fuel and 0% carbohydrate as a fuel. So the y-axis for that crossover graph of fuel utilization is this. It's percent of fat versus percent of carbohydrate. So as an extra credit graph, you could try to make that crossover graph of fuel utilization. That would be fun to look at. And then to complete this graph, you have 5 discussion questions. And these discussion questions need to be in your own words. Certainly use our book and use my notes and use the online resources. Please cite where you find this information. And some information you will look up, like what is the definition for a MET. We know that mathematically 1 MET is equal to 3.5 milliliters of oxygen per kilogram body weight per minute. And then some of the other questions will be to look at the data and look at your graph. And are these R values? Is that what we predict? Did they start off low, like a close to 0.7? And when the person exercised at higher exercise intensity, did they go up? I'm not exactly sure. You'll have to do that calculation. And then you'll describe the substrates. So were they using more fat or using more carbohydrate? And then you'll use the data table at the bottom of this graph to look at the percent of fat and the percent of carb at each stage. So at rest, at easy, moderate, and then hard intensity exercise. And then try to think about if this person that we tested in the lab, if they were an elite level aerobic athlete, an elite level cyclist, would these R values be different for this person if they were an elite aerobic athlete? So a fun little lab experience with some data that I've collected from the exercise physiology lab, and I've shared that data with you. You'll have some relatively simple calculations to do. Just make sure you don't make a mistake someplace and sort of look at your numbers to make sure they look realistic. And then at the bottom of the lab, 5 different discussion questions, and then 1 assigned graph, and then 1 extra credit graph. And try to cut and paste everything into this one document, and then save this document, and then upload it into Blackboard as your lab assignment. So again, in conclusion, this was our second lab experience. And a nice little lab and a nice little way to look at fuel utilization during exercise and during exercise intensity.